Hello there, ATS EVS students. Dr. John Schrage here, and we've made it through a lecture that was all about radiation laws, what determines how much radiation is being emitted, and what radiation was, and what kinds of radiation there are, and what determines what kinds of radiation the object emits, and how much, and so on. Let's actually try to figure out what that means from a climate perspective, in terms of what can radiation actually do in Earth's climate system. We are trying to understand, how do we know what we know about the climate system? And one part of the climate system that we understand very well is radiation. This is all thoroughly grounded in experiment and theory and derivations mathematically and so on. And that's where we got rules like Wien's law and Stefan Boltzmann's law and so on. These are very well established physical principles. In the last lecture, we talked about how you can think about radiation as like waves in the electromagnetic field. And that is a good way to think about radiation in the sense that it helps you understand this idea of wavelength. Remember, wavelength is the property that is describing what kind of radiation it is. There's shortwave radiation that principally comes from the sun, and there's long-wave radiation that principally comes from things of terrestrial origin, the Earth, the atmosphere, clouds, greenhouse gases, things like that. But the only difference between all the different types of radiation, whether they were gamma rays, X-rays, ultraviolet radiation, visible light, infrared radiation, microwaves, radio waves, whatever, the only difference between them is their wavelength. So, but they're all just waves in the electromagnetic field, and everything around us creates these waves in the electromagnetic field. They are created when an object emits radiation. Everything around us emits radiation. It's part of what it means to be matter. And so, whether that is something like this light bulb that is emitting shortwave radiation in the form of light, or for that matter, the sun, which emits shortwave radiation in the form of light, or whether it's you, where you are currently emitting a lot of long-wave radiation, mostly in the form of infrared radiation and microwave radiation and so on. But everything emits radiation. It's hard for you and I to see the radiation that, say, I'm emitting from my hand right now, but that's because we don't have eyes that are evolved to see radiation at those wavelengths. If we had eyes that were evolved to see infrared radiation, you would see that you are glowing like a light bulb right now. In fact, as your book points out, the total amount of energy you're giving off is actually pretty close to the same amount that a light bulb would be giving off. Everything emits radiation, and it generally emits, it always emits radiation over a range of wavelengths. We saw diagrams like this one in the previous lecture, where we were saying, hey, this is a graph that shows over a range of wavelengths along the x-axis, how much radiation is being emitted at that wavelength by an object of that temperature. This happens to be a graph for the sun. The surface of the sun is a temperature of about 6,000 Kelvin. And we see that it emits a whole lot of radiation with wavelengths around 0.5 microns. Remember, a micron is a millionth of a meter. But it does, in fact, emit radiation over a range of wavelengths. That being said, though, there is a wavelength of maximum emission, that peak of that curve. Where was the most radiation being emitted? And that wavelength of maximum emission is determined by the temperature of the object doing the emitting. That was Wien's law. Wien's law tells us that the hotter an object is, the shorter the wavelength of maximum emission. This was the core behind the story of why the sun emits shortwave radiation, whereas objects at the surface of the Earth, like the ground, the ocean, clouds, the atmosphere, things of terrestrial origin generally emit long-wave radiation. Things at the surface of the Earth are just a whole lot cooler than the surface of the sun. Excuse me, I have a tickle. And we illustrated Wien's law in a number of different ways. I like this particular diagram from the previous lecture, where I showed you the wavelength of maximum emission for 4 different objects of different temperatures. Now, I this time colored the dots slightly different colors to help you see the temperatures better. The coolest object here is the one that I highlighted in blue, where its wavelength of maximum emission is right around 3 microns. It's still 1,000 Kelvin in this case. It's hardly cool, but whatever. The next warmest object was 1200 Kelvin, and I marked its wavelength of maximum emission in green, which was about, 2.5 microns. And then at 1400 Kelvin, I marked it, and it was about 2 microns. and then at about 1600 Kelvin, the object was about, I don't know, maybe 1.8 microns or something was its wavelength of maximum emission. The hotter the object got, the shorter the wavelength of maximum emission. The object tended to be mostly emitting shorter wavelengths of radiation. The total amount of radiation that the object is emitting also comes from the temperature. That was Stefan Boltzmann's law. Stefan and Boltzmann were two scientists in Europe in the late 1800s who independently discovered this relationship, that objects emit radiation proportional to the fourth power of temperature. In other words, the hotter the object gets, the more radiation it gives off. And in fact, the amount of radiation it gives off gets bigger and bigger and bigger, faster and faster and faster. So, you know, if you think back to that previous slide, the temperature of those objects was getting higher and higher, and the area under the curve, which is the total amount of power being emitted by the object in the form of radiation, was getting big faster and faster and faster. Emitting radiation is what matter does. It is part of what's happening at a quantum level inside of the molecules and the atoms and so on, which we are not going to get bogged down with. Objects that are made of matter emit radiation. And doing so takes energy. Creating waves in the electromagnetic field, / emitting photons, whichever terminology makes you happier. Creating waves in the electromagnetic field takes energy. It removes internal energy from the object that is doing the emitting. When the sun gives off shortwave radiation, it extracts energy from the sun and puts it in the form of those waves. Think about, like, if you've ever been to like a wave pool at a water park or something like that. Some big motor is being used to produce these big waves in the pool. It takes energy to produce those waves. And in the same way, internal energy from inside of the sun or inside of your body or whatever is being used to produce those waves of electromagnetic radiation that you are emitting. Extracting internal energy is a way of saying cooling the object down. As you emit radiation, in your case infrared and microwave, other forms of long-wave radiation, that is extracting internal energy from your body and emitting it in the form of long-wave radiation out into the world around you. So, for example, the sun, we are extracting energy from the sun and putting it in the form of shortwave radiation that heads out into interplanetary space, some of which actually reaches the surface of the Earth. Meanwhile, the surface of the Earth is emitting long-wave radiation, which is headed up through the atmosphere and out to interplanetary space, taking energy with it, extracting internal energy from the surface of the Earth, and, that is to say, heat, or temperature, or whatever, and extracting that and sending it up through the atmosphere and out towards space in the form of long-wave radiation. Emitting radiation is a big part of how the planet is going to be the temperature it is, and we know that the total amount of energy that is being given off is proportional to the temperature. I like this diagram right here that shows how the surface of the Earth is emitting radiation. This is from some satellite that was showing the amount of radiation the surface of the Earth was emitting. Now, they've actually converted it back by converting from the amount of radiation being emitted. They converted that back to a temperature, but we could have thought of this as being like, the darker and redder the colors are, the more radiation is being emitted. And you can see like the Sahara Desert and Saudi Arabia and India and Northern Australia and the deserts of the southwest United States are emitting enormous amounts of radiation because they're hot. By Stefan Boltzmann's law, they should be emitting a whole lot of radiation. Whereas places like the polar regions, Greenland, and so on, are emitting less radiation because they're cooler. Now, there's a whole lot of other structure in this diagram here that is about things like clouds and so on. Clouds are very cold and emit less radiation. There's a whole lot of stories on this diagram here. You know what's another thing that I always like to use when I'm picturing? Whenever I see a movie that's made by Universal, I love that opening at the beginning of the movie where they are showing, it's just the globe turning and you can see this like radiation coming off of the land masses up into space. Okay, I'm sure Universal has no thought that this is about radiation or something, and of course the radiation will be coming off the ocean and stuff too, but picture how the Earth is like shining with this long-wave radiation, because that is in fact what it is doing. That is what the satellites are seeing, is this long-wave radiation being emitted from the surface of the Earth and coming up through the atmosphere, extracting heat from the surface of the Earth and bringing it up through the atmosphere off toward interplanetary space. Now these curves that we've been seeing all through all this stuff here were for theoretical black bodies. Now again, I don't want to get bogged down with that term black bodies. That's a term that comes to us from physics. What it means as a black body is that this object is emitting as much radiation as it can at every wavelength. Real objects are not perfectly efficient emitters. They have a emissivity at every wavelength that says I'm actually, let's say, 50% efficient at emitting at this wavelength, and I'm 100% efficient at emitting this wavelength. And this is a very complicated idea about the nature of the molecules that make the material up and so on. But all these curves that we've seen so far have been for theoretical black bodies. In practice, a lot of things in the climate system are in fact black bodies and do emit more or less exactly what Stefan Boltzmann's law says, and more or less exactly what at the wavelengths that Wien's law says. The sun, for example, is actually a pretty good black body. It pretty much emits exactly like this curve. At every wavelength, it's emitting up pretty much exactly this amount. Not exactly, but pretty close. So different materials may or may not be perfect black bodies and may not emit exactly the right amount. Well, not the right amount, it is the right amount. It's just not exactly the amount predicted by theory. We've been talking about radiation being emitted by an object and how emitting radiation is a cooling process. It extracts internal energy from the object doing the emitting and sends it off into the world in the form of radiation waves in the electromagnetic field. In the same way, absorbing radiation is stopping the radiation that is passing through the object. And stopping these waves of radiation adds energy to the object doing the stopping. It increases the internal energy of the object doing the stopping. When you are outside on a sunny day and the sunlight is beating down on your skin, the materials in your skin are absorbing the shortwave radiation from the sun. Those molecules are taking the energy of those waves that are going by and extracting that energy. It stops the radiation, but it also adds internal energy to the object that did the absorbing. It warms the object up. It is a warming process. You could think of the same way, I talked about like a wave generator at a wave pool. There are ways to extract energy from waves, like to produce clean power, where they can actually use apparatuses that can extract energy from ocean waves and tides and things like that as a way of producing electricity. Stopping waves, extracting the energy from them, is a way of getting energy, or in this case, internal energy, that is to say, warming the object up. Now, I want to actually introduce a vocabulary word here that you're probably not familiar with in this context, and it will be very helpful to have this vocabulary word. And that is this word incident. We're going to talk about incident radiation. Incident in this context is actually the second definition that comes up if you Google define incident. It's when something falls on or strikes something. Like incident radiation is the radiation that is falling on or striking on a surface. Sunlight is incident upon the surface of the earth, or it is incident upon the clouds. There is a certain amount of long-wave radiation that goes up from the surface of the earth and becomes incident on the clouds that are between the surface of the earth and interplanetary space. Incident just sort of means like came into contact with. I like the idea of falling upon or striking. So incident radiation just means like we're talking about the part that the amount of radiation that hit the object. When we set up solar cells on the roof of a building, okay, we're talking about the amount of solar radiation incident on the solar panels. All right, it's just a term that comes to us from the study of radiation. And so we could talk about like the incident radiation on from the shortwave radiation that falls on this field here. The ground is really good at absorbing, well, shortwave radiation from the sun. Maybe not the ground itself, although the ground can be plants, for example. Their leaves are in the business of absorbing incident shortwave radiation. That's what leaves do. They catch, they're little solar panels. They catch solar radiation as it goes by and they absorb it, and they use the energy in those photons of shortwave radiation to produce sugars and things like that that are the food for the plant. The food in your microwave. When you put food into the microwave, it is absorbing the microwave radiation that is being emitted by the magnetron in your microwave oven, and then absorbing that microwave radiation makes the food hotter. It increases the internal energy of the food. which is another way of saying makes hotter. Now, when everything in the universe emits radiation, the sun, clouds, greenhouse gases, the atmosphere, the ground, oceans, ice sheets, whatever, they all emit radiation. When radiation hits an object, when it is incident upon the object, it can be absorbed. That is one of the things that can happen. But there are in fact 1, 2, 3 other things that can happen when radiation is incident upon an object, where the object might be a cloud or the ground or whatever. The incident radiation can be transmitted, it can be reflected, or it could be scattered. And we're going to talk about each of these 3 possibilities shortly here. Okay. In the Intro to Meteorology class, ATS 113, if you stick with that, we actually spend even more time on this idea, and I teach you this little acronym to help you remember this. It's RATS. R-A-T-S. Radiation can be reflected, absorbed, transmitted, or scattered. RATS. Okay? We aren't going to get too bogged down with all of this stuff this semester, so I didn't want to get all, we'd spend a lot of time in the intro talking about these things. Now, transmitted. Radiation that hits an object can be transmitted by the object. Transmitted actually means something different than what you might be thinking. Transmitted means that radiation just passes through the object. I know that, like, for example, when you talk about your cell phone and it transmits a signal, that means, like, it sends the signal out. No, in the context of radiation, what we mean when we say transmitted is we mean that the radiation went through. Like, the air transmits the signals from your cell phone. Your antenna emits the signals, they are transmitted through the atmosphere to the tower that picks your signals up. In general, most shortwave radiation is actually transmitted by the atmosphere. In general, light is able to pass through air. We wouldn't be able to see if it didn't, right? By and large, light is transmitted by air. Most forms of shortwave radiation are transmitted by air. There are some exceptions. For example, ultraviolet radiation is not well transmitted by some gases in the atmosphere, like ozone. Ozone is a gas that absorbs ultraviolet radiation, but we're going to talk about that more in just a few minutes. But that's a good example of transmitted. So, like, sunlight is transmitted through the atmosphere so that it can, pass through the atmosphere and reach the surface of the Earth. Radio waves. Radio waves are, in general, transmitted through walls. If you are inside, you can still use your cell phone. Cell phones use radio waves to transmit from their antenna to through the air over to the tower. Those radio waves are transmitted through walls that are in the way. Same with, like, if you're in the house, you can listen to the radio or watch television using an antenna. The radio waves that are used to transmit radio programming and television programming and so on, to a good approximation, are transmitted through walls. You can still pick up radio signals through the walls. Same with, like, Wi-Fi signals and so on, their type of radio as well. And they can be transmitted through walls, to a good approximation anyway. Obviously enough walls and they start having problems. A second thing that can happen with radiation when it is incident upon a surface is that it can be reflected. Snow is a great example. Snow on the ground reflects an awful lot of shortwave radiation. To use a power vocabulary word we're going to see in a few minutes, the reflectivity of snow is very high. Snow is very bright white. Shortwave radiation from the sun that hits the snow isn't in general absorbed by the snow and warms the snow up. In general, shortwave radiation that hits the snow is reflected by the snow back up into the air. Another good example is clouds. Clouds are really good at reflecting shortwave radiation from the sun. If you are outside on a hot day and it's sunny and it's hot and the sun's beating down on you, and then a cloud passes between you and the sun, and you're in the shade for a while, you're not so hot. Because this cloud is reflecting some of the shortwave radiation from the sun, rather than letting that shortwave radiation hit you, become incident upon you, and then you absorb that radiation, right? Clouds reflect a great deal of shortwave radiation, and this is going to have climate implications. If clouds are reflecting shortwave radiation before it even gets to the ground, that's radiation that is lost. That's energy that was never used to warm the surface of the Earth. We're going to have to be able to take that into account if we're trying to understand climate change. There's a powerful vocabulary word that we actually need when we're talking about reflection of shortwave radiation, and that word is albedo. Albedo is the fraction of all the incident shortwave and, well, specifically visible light that is reflected by an object. So it's a measure of how good that object is at reflecting visible light. Snow has a very high albedo. Most of the visible light that encounters a snowy surface is reflected off of the snowy surface. Clouds have a high albedo. On the other hand, something like asphalt, which is quite dark, has a very low albedo. Or coal, or a freshly plowed field, or something like that, would have a very low albedo. Relatively little of the shortwave radiation that hits those surfaces is reflected. Albedo is a number between 0 and 1, where 1 means it reflects all of the visible light that hits it, and 0 means it reflects none of the visible light that hits it. The key, though, here is to understand that this means for visible light. Albedo does not apply to like long-wave radiation or something like that. It's specifically about visible light. A good rule of thumb, if you're trying to approximate to yourself as to what you think the albedo of a surface is to think in terms of a black and white picture. If you could think of that same scene in a black and white picture, and we'll see some examples of this in a little bit, black and white pictures are actually very close to understanding the albedo of an object. If an object is going to appear dark in a black and white picture, it has a low albedo. If it's going to appear bright on a black and white picture, it's going to have a high albedo. It's reflecting a lot of the shortwave radiation that hits it. Now, of rats, RATS, reflected, absorbed, transmitted, the S is scattered. Scattered is hugely important in meteorology. Scattering is when radiation hits an object and then reflects off of it. Well, not reflects, is scattered off of it. Reflects means it kind of goes back the direction it came. Scattered means like heads off in a new direction. And scattered is hugely important in like a number of meteorological phenomena. Scattered is why the sky is blue. Scattering is why the sky appears red at sunset. Scattering is why foggy days, it's hard to see on foggy days. There's a lot of interesting meteorological applications to scattering. As it happens, scattering is not very important in a climate context. So we're going to set scattering aside. We don't need scattering so much at this point in our education. Stick around for ATS 113 and you're going to learn all about how scattering is important in meteorology, but it is not hugely important for climate purposes. What if we want to actually measure this? If there's going to be all these climate consequences to how much radiation is being reflected by clouds or absorbed by the ground or transmitted through the ozone layer or whatever, we need a way to actually describe that. That's how science works. We need a way to quantify how much reflection, how much absorption, how much transmission of radiation is happening. Objects have a set of properties called the reflectivity, the absorptivity, and the transmissivity. Those are hard words. Reflectivity is given by the letter R, absorptivity is given by the letter A, and transmissivity is given by the letter T. By the way, for point of fact, absorptivity and emissivity turn out to be the same thing. How good you are at absorbing radiation is exactly the same as how good you are at emitting radiation, which is a curious little bit of physics called Kirchhoff's law, but we won't go there just yet. These R and A and T letters here are all kind of like albedo. They are a unitless number between 0 and 1. If the reflectivity of the object is 0.5, that means it reflects half the radiation that is hitting it. Or if the transmissivity of the object is 1, that means all that radiation goes right through the object. It isn't absorbing or reflecting any of it. They're just unitless numbers from 0 to 1. They have a lot of interesting properties. For example, A plus R plus T has to equal 1 for all objects. If the object is opaque, that is, radiation doesn't transmit through it, then A plus R has to equal 1. There's a lot of interesting properties that we're not going through at this point. But there's a subtle problem here. Objects don't necessarily reflect radiation the same amount depending on the types of radiation it is. An object, it's perfectly possible that an object is great at reflecting visible light, but not good at reflecting long-wave radiation. Or good at transmitting long-wave radiation, but not good at transmitting ultraviolet radiation, or something like that. There really should be a wavelength dependence here. A and R and T really ought to be a function of the wavelength of radiation we're talking about. Now, here's a great big word that'll be useful to you in crossword puzzles someday, monochromatic. Monochromatic is the right word for physics that means at a particular wavelength. So, we use this little, remember lambda was our symbol for wavelength? So we put a little lambda by the R and the A and the T here to talk about monochromatic reflectivity. That means at the particular wavelength I'm talking about, let's say 0.9 microns. At 0.9 microns, what is the reflectivity of this object? If radiation with a wavelength of 0.9 microns is incident upon this object, how much of it will get reflected? And then if we're talking about 0.9 microns, it also has a monochromatic absorptivity. How good is this object at absorbing radiation that has a wavelength of 0.9 microns? Or how good is it at transmitting radiation that has a wavelength of 0.9 microns? This is going to be really important for climate change because the greenhouse gases that are probably responsible for the climate change that we're seeing have very complicated absorptivities and transmissivities and reflectivity is not so much an issue with that, but they're going to be very good at absorbing and emitting radiation at some wavelengths, and they're going to be very poor at absorbing radiation or emitting radiation for that matter at certain wavelengths. Their absorptivity will very strongly depend on what wavelength of radiation we're talking about. If we're talking about shortwave radiation, if we're talking about longwave radiation, if we're talking about the difference between infrared radiation and microwave radiation, the greenhouse gases are going to have complicated relationships to their absorptivity is going to change depending on wavelength. Lots of things can do that. For example, in general, air. In general, air at visible wavelengths, like light, the transmissivity at those wavelengths is generally very high. Let's pick a wavelength of radiation. I think about 0.5 microns is a good number. Okay, 0.5 microns is a particular wavelength of light. The monochromatic transmissivity for 0.5 microns for air is very high. Basically all of the point wavelengths of radiation, all the photons of radiation that have a wavelength of 0.5 microns pretty much make it through the air, no problem. 0.5 microns refers to a particular wavelength of the light. It's a particular color. If we actually went back and looked at the electromagnetic spectrum, I have to admit I can't remember what color it is. Let's just say yellow. Okay? Yellow light is transmitted very well by the atmosphere. Maybe the monochromatic transmissivity of the atmosphere for the color yellow is probably pretty close to 1. Almost all of it is transmitted. By the way, can you see how then the word monochromatic works? Monochromatic, we're referring to one color. Okay, color being useful if we're talking about wavelength of light, right? Different wavelengths of light are different colors. In the same way, the absorptivity of the atmosphere for that one particular wavelength of visible light, like yellow at 0.5 microns, is very low. Air molecules in general don't absorb yellow light. Yellow light travels through the atmosphere. Okay, this light just passes through the atmosphere. On the other hand, the story is very different for different wavelengths of light. Of radiation. How about infrared radiation? Infrared radiation is at longer wavelengths. Let's just say 1 millimeter. Okay, that's a fairly long wavelength of radiation. Air has different monochromatic absorptivities and monochromatic reflectivities and transmissivities and so on for radiation at that wavelength. The transmissivity can be very low. Air is awfully good at absorbing some wavelengths of infrared radiation, and the photons don't get through the air. Or, so the transmissivity can be low, or the absorptivity at those wavelengths can be very high. The air just does not allow that infrared radiation to pass through it. Infrared radiation, in general, is absorbed by air molecules. Very little infrared radiation makes it through the atmosphere. If you have a source of infrared radiation, by the time you're even a little ways away from it, most of that infrared radiation has been absorbed by the air between you and the source of infrared radiation. There's a powerful vocabulary word here. We could then describe air as being a selective absorber. It is a good absorber at certain wavelengths of radiation, and it is a poor absorber of radiation at other wavelengths. Greenhouse gases are going to be amazing selective absorbers. They're going to be really good at absorbing certain kinds of radiation and keeping it from leaving the Earth and getting out into interplanetary space. And they're not going to be very good at absorbing radiation at other wavelengths. We're going to have to sort that all out. But before we get into the second half of this lecture, I want to ask you a couple questions about what we've seen so far. Because there certainly has been a lot of vocabulary so far in this lecture. Okay, think about a window. Window glass lets in the light from the outside world. Light comes through the window. but it blocks infrared radiation. That's part of how they make windows. They're treated with a coating that blocks infrared radiation. That way, like on a hot summer day, the hot objects outside aren't emitting radiation. Well, they are emitting radiation, but that radiation can't come through the window and warm up the inside of the house. For this glass, then, A, the monochromatic transmissivity for light is greater than the monochromatic transmissivity for infrared radiation. B, the monochromatic transmissivity for light is less than the monochromatic transmissivity for infrared radiation. Or C, the two monochromatic transmissivities are equal. Oh, alright, so we're picturing window glass here. The light comes through, but the infrared radiation doesn't. What do we say about the properties of this window glass? Take a look at your three options. Choose one of the three options below this video to get a little feedback before we move on to question 2.